Dear students, welcome to our class on Micrometeorology of Crops, Solar Radiation 5. So in this class, we are going to understand what is short wave radiation, what is long wave radiation, how a leaf can escape from the heat load when long wave radiation falls, and some basic things what with reference to photosynthesis also we try to understand. Now we start our class with a very small statement, okay, like you see, long wave exchange between the crops and the atmosphere. See, long wave exchange between the crop and the atmosphere. So atmosphere is a colorless, odorless and tasteless physical mixture of gases enveloping the earth on all sides. So such an atmosphere definitely interacts with the crops because we, the agrometeorologists, raise the crops in the field. The crop, how it responds to the atmosphere, how it interacts with the atmosphere. It interacts with the atmosphere basically in two ways. One is short wave radiation, and the other one is the long wave radiation. Short wave radiation, usually we refer to the radiant energy that we receive from the sun, for the reason that the long wave radiation from 3 to 100 microns, okay, long wave radiation from 3 to 100 microns, most of it is after we receive from the sun, and when it is falling on the earthly bodies, and then it is going with the long waves, so that the atmosphere gets heated up. Before that, the atmosphere also gets heated up when long wave radiant energy is coming from the sun through the troposphere. Of course, troposphere, stratosphere, mesosphere, ionosphere and exosphere. So from exosphere to troposphere, and it is reaching, it also gets heated up. But the process of long wave radiation dynamics, once it falls on the earthly object, and of course reflected is there to some extent, no doubt, after absorption, emission. So based on the Kirchhoff's law, it goes into the atmosphere. That is a major portion as far as the long wave radiation is concerned, not that much from the sun directly. Now with this background, I would like to discuss with you, okay, that the leaf, you are seeing a plant, this is the leaf. A leaf absorbs strongly in the long wave infrared radiation, of which there is no major input from the sun. That's what I told. From the sun, there is no major input from the long wave radiation. So how long wave radiation generates? I told you half a minute back. Now, as a consequence of Kirchhoff's law, what is Kirchhoff's law? A lambda is equal to E lambda. Okay. So as a consequence of Kirchhoff's law, it is a good radiator in that wave band and is able to dissipate the energy. In which wave band? In the long wave band, the leaf acts as a good radiator. So it escapes the heat load, long wave radiation heat load, So that escapes by, as I told few times in the last one or two classes, first one is the radiation, second one is the convection, third one is the stomatal functions, closure and opening of the stomata. Now, see, the description of long wave radiation exchange and particularly the downward flux of IR radiation. See, two scientists have worked out extensively. First one is the J.L. Monteith, with whom I had an opportunity. Okay, he was working with the University of Nottingham, Sutton Bonington, Loughborough, UK. I had a great time in learning this science from him. And Swinbank, of course. As far as our today's topic is concerned, among all the excellent contributions of Professor J.L. Monteith, the upward flux, okay, he had estimated upward flux of the long wave radiation. Swinbank estimated the downward flux. As far as my interaction with Professor J.L. Monteith in University of Nottingham, Sutton Bonington, Loughborough, UK. Okay, there I learned from him that it is absolutely difficult to estimate langward flux upward and also downward. However, they have done excellent approximations using mathematics and calculus. This much I can tell. Why I am telling is, now today's topic is long wave exchange between the crops and the atmosphere. Long wave exchange. Crop is influenced by long wave. So that's why crop gets heated up. It has to dissipate. Unlike you and me and animals, it cannot move to any other place. By anchoring itself onto the root, on the soil, it has to survive. So it has to dissipate heat. That's why long wave radiation has got an importance. Now here, as far as the works of Professor J.L. Monteith in University of Nottingham, Sutton Bonington, there is a wonderful finding. If we assume a crop to be an ideal black body in long wave infrared radiation, then the crop would lose 107 watts per meter square, 107 watts per meter square on a cloudless sky day at 0 degrees centigrade. At 0 degrees centigrade. This was the finding. That's what I had learned from Professor J.L. Monteith. Here, the significance of it is very, very interesting. What is its significance? See, there are three terms: radiant flux density, irradiance. What Professor J.L. Monteith taught me was, Murthy, radiant flux, the energy coming from the sun. Radiant flux, watts, it has units of watts. Radiant flux density, watts per meter square. Irradiance, radiant flux density in a second, or in a second only, he told. So that would be a good approximation to understand the long wave radiant exchange between the crop and the atmosphere. That's what. Now here, most of the photosynthesis. Another important thing we try to understand: leaf photosynthesis and short wave radiation. Then we try to understand long wave radiation. As far as photosynthesis is concerned, short wave radiation, leaf photosynthesis. You see, if you go for a graph, this bit will come several times. This bit will come. Okay, in a graph, wavelength, which is compared for quantum yield. In a graph, wavelength is compared with which component? The component here is the quantum yield. This bit had come few times in the SRF. Okay, so if you take the relationship between the wavelength and quantum yield, here the quantum yield in the graph is relative units, not other units, relative units. See, if you take the wavelength on the x-axis, quantum yield on the y-axis, the photosynthesis, okay, the leaf photosynthesis, if you take the relative thing, in the 440 or 400 microns, and say approximately 620. Now 440 and 620 microns wavelength on the x-axis, if you see, and if you see this side quantum yield, the blue part is the blue part, and here the red part, blue and red part, 440, 620 wavelength nanometers. Okay, and the y-axis is the quantum yield. If you see, the blue part is 70% of the red, 620. Okay, that means even within the quantum yield, with reference to wavelength and quantum yield, this bit will come. Wavelength and quantum yield, when there is a comparison, blue 440 microns and this particular red 620. If we see, of course, red and far red, okay, that is an entirely different story. Here, within this 0.4 to 0.7 microns of the light, these two themselves are 30% differing. This particular blue is only 70% of the red part. There is again a shoulder. After the 620, there is again a small shoulder like. What I mean to say is, wavelength and quantum yield is not uniform as far as photosynthesis of leaf is concerned. Again, in a very simple, okay, general terms, I would like to say, all VIB, war will not respond equally, okay, as far as the leaf photosynthesis is concerned. Photomorphogenesis, photosynthesis, photogenic, different physiological processes differ with reference to the spectral distribution of radiant energy falling on the leaf. This is the take-home word I would like to share with you. Now, simply, I would like to share after last 2 minutes something related to photosynthesis. As we are all aware, there are two reactions. light reaction, dark reactions are there in the photosynthesis. The light phase, which is directly dependent upon the energy of the PAR. See, light part. In the basic course I told, ultraviolet radiation has got 9% energy, light part has got 41% energy, infrared part has got 50% energy among all the three basic of the solar spectrum. Okay, now here, okay, the light reactions are responsible for converting radiant energy into chemical energy in the form of ATP and NADPH. Okay, now as far as the dark reaction is concerned, in the dark reaction, the ATP and NADPH are okay. There is a chemical, the chemical energy of ATP and NADPH, okay, bring about the construction of carbohydrates and other essential products. So why I am telling is, I have taken 5 classes of micrometeorology, crops and solar radiation. 5 classes. This is the 5 class. In 2 minutes I am going to complete it. You should understand what Radha Murthy told. Okay, simply when energy is falling in, there is a short wave and there is a long wave radiation. There is a light part in it which has got 41% of the energy. That particular 41% of the energy, which we call it as the PA, photosynthetic active radiation, it is trapped by, okay, only 1% of the photons falling on the crop is utilized. The remaining 99% are dissipated by the leaf or a crop. Here, take home is that in the 5 classes, yes, radiant energy is there. It is following certain rules and certain laws. And as far as first law of thermodynamics is concerned, if you take a crop field of 1 acre, the energy entering is equal to the energy stored and energy leaving. Okay, that's what Kirchhoff's law is concerned. A lambda is equal to A lambda. So these laws are proven laws. Now here, the last 1 minute of the class, I would like to discuss with you very, very interesting thing. Light and crop photosynthesis. You may put a question, Murthy, okay, how to measure the light? So I used for my M.Sc experiment in Punjab Agriculture University, Ludhiana, a technique developed by Murthy and Sakai. Okay, in the year 1950, they published a paper. So when I was studying in early 1980s, I was in constant touch with Professor J.L. Monty, the University of Nottingham, Sutton, Bonington, Loughborough, UK. So from his knowledge and then from the works of Murthy and Sakai, it is a proven technique even now. I encourage all my beloved students who are interested to work on the micrometeorology of crops. I have faith. I am not asking you to accept it. Climate change is inevitable. Certainly, micrometeorology is going to address many of the problems of the crops, not only crops, for animals and also for the plantation crops, which are more than one season crops, perennial plantation crop. Micrometeorology is going to do excellent role. So that's why I am covering this one here. Last half minute I would like to share with you what is the technique that I used, what is the technique I suggest you also to use in your M.Sc PhD. Very simple, Murthy and Sakai. So if you take a crop, if you take a crop like this, for example, B.Sc law. What B.Sc law says? The relative radiation intensity decreases exponentially with increasing leaf area. Okay, that is the B.Sc law. B.Sc law, B-E-R-S, B.Sc law. What B.Sc law says? The relative radiation intensity. Sun is there. It is falling on the relative radiation intensity decreases exponentially with increasing leaf area. So Murthy and Sakai have developed a wonderful technique that if you presume this is a crop, you divide the crop into different slices, 10 centimeters, 10 centimeters, 10 centimeters, depending upon the height. So what is the energy entering? What is the energy leaving? You know the I is equal, you know this equation, I is equal to I0 e to the power of minus kf. Okay. I is the energy that is present in a particular layer. I0 at the top. Okay, E is equal to Neperian base. K is the F is the leaf area index. K is the extension coefficient. I is equal to I0 e to the power of minus kf. That is the Beer's law. The relative radiation intensity decreases exponentially with increasing leaf area. That means how much energy is trapped in each layer. That is very, very interesting to measure. I have learnt both from my teachers in PAU Ludhiana and also from Professor J.L. I used it for both my M.Sc and Ph.D. thesis. I also suggest you to follow as far as light and crop photosynthesis is concerned. All the micrometeorologists who are going to address the problems of climate change to know to read the Monson 1953 paper, the works of Professor J.L. Mantitha, and again, of course, use this one for solving the problems of climate change. Thanking you very much.